Okay, we're getting ready. We have our last talk of the session that Philippe will give on translation of temporal logic. And please take it away.
Thanks for the introduction. Can you hear me? Okay. Yeah, so I'm going to present you how we translate temporal logics efficiently for infinite state reactive synthesis. So why do we even care about infinite state reactive synthesis? So I mean, as we already seen this morning in the keynote, right, in synthesis in general, like there's a problem where you want to automatically generate some implementation from some kind of high-level specification that kind of describes how correct behavior of the system looks like. And one major historical direction has been program synthesis, as we've seen it in this morning. And in program synthesis, what you want to get is a classical program, in the sense a program that gets some inputs, does some computation, and produces some outputs. And that's why, like, usually a specification for such a classical program is via the relationship between the input and the outputs. And usually you have something like a grammar that defines how a well-formed program looks like. In some sense, right, what you generate is some kind of like data transformation. And since you often have like some data variables and so on that have like some integer types or something like that, you have an infinite state problem. The other direction is finite state reactive synthesis. There you want to generate a finite state controller. Think of something like a Mealy machine that runs over time and interacts with its environment. So it gets some input, produces some outputs, gets some inputs, produces some outputs. And that's why like one natural specific way of specifying such system is via temporal logics, right? Another way is like, for example, via two-player games. And the main technique to do synthesis in this setting is via game solving. So either you have a game directly or you translate the temporal logic formula to a game and then you solve the game. But now if you think about it, many actual problems, they need both, right? You have both like this infinite state, so you want to work with data variables, you want to work with integers and so on. And at the same time, right, you have this aspect of abstract control and running over time, right, interacting with the environment. And since like temporal logics provide us like this high-level way of specifying things, we want to actually look at temporal logics in this context of infinite state synthesis. And that's why, like, recently this problem has attracted more attention, right? There's a wider body of work that has been done towards that, but very recently there has been like two approaches that work on an extension of LTL with like also with data, right? And what they do is, right, they take this extension, right, they abstract back to LTL, and then they use the finite state synthesis problem. Similarly, like there have been like ways of doing symbolic game solving, where you take like the finite state game solving algorithm, and then lift it symbolically to work also in the infinite state, to handle the data that you have symbolically. However, like both of these kind of approaches, they have the problem that they kind of lift this finite state problem kind of to the infinite state problem. And then in an infinite state problem, you have like phenomena that you don't really have in the finite state. So they are like, this can be limited. That's why at last year's POPL', we introduced like a dedicated technique to kind of tackle this infinite state game aspect. So and as you can see, right, there have been other things in the meantime, right? So there have been improvements on the game solving side for the infinite state problems. But of course, as I already told you, right, we want to actually also be able to work with logic. And that's why in this work we looked at how to efficiently translate these temporal logics that talk about this infinite state space to symbolic games. Okay, just to quickly, I always mentioned like how nice logic is. Just a quick example to really make the point, right? This is like an LTL formula that tells you if infinitely often A holds, then infinitely often B and infinitely often C have to hold, right? So this is like very nice to write, but if you want to write like a game or automaton, it might look like that, right? So you really don't want to write the lower one if you can write the upper one, right? Okay, so this is like now our logic that we work with. We call it reactive program linear temporal logic. So like you have like, of course, you have Boolean operators and you have the standard temporal operators that you know from LTL, right? If you don't know, right, you have, for example, the next operator, which tells that something they talk about time, that something has to hold at the next step. The globally operator that tells something has to always hold, or the eventually operator that tells you something has to hold at some point. right? And then we have predicates. So predicates are quantifier-free first-order logic formulas over some state variables, some input variables that come from the environment, and next state variables, right? So we have from some state, and we want to be able to relate the current state with the next state. Yeah, and if you have some state, right, the inputs are chosen by the environment, and the next state variables are chosen by the system, right? So there you have this interaction between the system and the environment. And do synthesis, what we do, we translate. We take such a formula, we translate it to a game, and then we want to solve it. So the solving aspect is kind of already covered by kind of previous works. So in this work, we really want to really focus on this translation aspect. So now there's a way to actually directly translate such a formula to like a symbolic game by using the translation over LTL. So what we do, let's take our example formula where we say, okay, we have some state variable x that should always be incremented, and infinitely often it should be greater than 0. Now we can replace those two predicates by propositions and get an LTL formula. Then we can use a standard construction to get like an automaton, like in this case a Bücher automaton for this formula. And then we can do kind of the back translation, right? We replace these predicates back by, so the propositions backed by the predicates, and then we get this, and then we can get a game out of this. Here it's a one-player game, but like if you would have inputs, it would be basically the same. And now I claim that we have, during this translation process, we have actually lost some kind of information. So why is that? Well, like now if you just look at this formula, just think about it, right? I mean, this is somewhat redundant, right? Why? Well, if we always increment x, then at some point, x will be greater than 0, and once it is greater than 0, well, it will always stay greater than 0. So it will also be infinitely often greater than 0. So in some sense, we could drop this right-hand part, right? I think this is fairly obvious in this formula, but I claim it's not very clear in this game, right? And if you think about it, this is still a simple example, right? If you get to something more complex, it might be even less clear. So the question is now, how can we apply this reasoning to games? Okay, so that's where our method kicks in. What am I doing? Okay, we start with the temporal formula, and then of course, we do this direct translation to get a symbolic game. And what we also do is we construct some kind of monitor. You can imagine it's something similar to automaton, but it's not an automaton. And this monitor uses some kind of theory information and this temporal structure of the original specification. And with that, it can use for some finite prefix, it can give us a verdict. And this verdict, right, we can use, right, we will construct a product from the monitor and the symbolic game to get an enhanced game. And this verdict will help us to get a smaller game and to kind of simplify the winning condition, such that like if we then solve the game, right, it will be hopefully simpler to solve. Okay, now how do we construct this monitor? Let's go back to an example. So this is like a variation of our previous example. Instead of adding 1, we add d, and this d should initially be greater than 0, and from this point on, it should not change. Okay, so when we do this by doing some expansion and applying some rules. So we start our initial state of our monitor is this formula, and we have, what's important to note, we have these phi sets that kind of are things that we track that kind of always hold, right? Or initially we know that d should always stay the same. Okay, and now we can apply a rule. What we can see is like if d always stays the same and initially d is greater than 0, well then it's an invariant, right? So it will always stay greater than 0. You can check that with an SMT query. And now we can add this information here that d will be greater than 0. Okay, then we can compute kind of the next state, right? What happens after one step? For example, if d is smaller or equal than 0, right, then this whole formula becomes true. If it's greater than 0, but we don't keep it the same, formula becomes false. And otherwise, right, like the second part here now becomes relevant. So we add x prime equals x plus d. We add this to the things that have to always hold. And now, infinitely often, x should be greater than 0. Okay, now here we can apply a second rule. So what you can see is, right, if d is greater than 0, and we always add d to x, right? So we always add at least 1. So we know that, like similar to our previous example, at some point x will be greater than 0, right? And this is a bit more complex check. Now this is kind of a fixed point computation, but with this we can derive that also from this point on, like x should be, or eventually x should be greater than 0. Okay. Now if you look at that, right? This part now is under globally, so infinitely often x should be greater than 0. So in some sense, this part now here is redundant, right? And now we can also remove that and get the simpler formula. Yeah, and then we can like add the missing transitions, right? And here it's important to note if d stays the same and we always add d to x, right? We will always stay in this part. Now the second step is to actually add this verdict that makes kind of the power of the monitor. So like if the formula is true or false, right, we know that the system will win for sure or lose for sure, so we get an unsafe or valid verdict. Then we have this safety verdict, and like this, what you can see, this formula without the derived parts is a safety formula, if you know what that means. But what's important to note here, right, it's fine for the system to, if it always stays in these blue parts, right, the system will win. So this is why this is a safety part. It's sufficient to stay here. Okay. So this is how we construct a monitor, and now we have these verdicts, these 4 different verdicts, and also and now we can construct a product. What's also important to note, right? This monitor construction is completely independent on how we constructed the symbolic game or how we will later use it. So it's like if you would improve that, right? You could still use this approach. Okay, so how do we combine that? So let's go back to our example. So we had our monitor here, and really the thing I want to highlight for this example, once we are in the safety part and this blue part, we want to stay here. Then we build this direct translated game, which looks something like that. And here, right, the goal is to infinitely often visit one of those 2 locations. And now we can construct a product, and this product will look like that. And now it's here important to note, right here we had a part where we had to alternate, right, and infinitely often do that. Now here, this is kind of the monitor has told us this is a safety part, so it suffices if we can just stay here, right? And so we get some easier winning condition, right? Because I mean it's a safety condition, and it's kind of easier to solve. Okay, so we also evaluated this because I claim this made stuff easier, but we also wanted to check it. So we built a prototype that uses Spot to translate the LTL formulas to automata. Because for the reasoning, we use Z3 as the SMT solver. As the underlying game solver, we use the game solver that we created for last year's POPL. And to these fixed points, right, we use MuVal, which is a tool for computing for solving fixed point equations. And we compared them to the other approaches that exist to handle these temporal logics with data, namely Raboni and Temos, which are these both like abstraction-based approaches that I mentioned earlier, and of course also the direct translation, just to see how this compares. And then as benchmarks, we used literature benchmarks as well as new benchmarks that encode some kind of more complex behavior, because those were many of them were still kind of simple. Okay, so this is an excerpt from our evaluation table. Here we have the literature benchmark. So as you can see, right, usually this monitor stuff adds an overhead over the direct translation in these cases, right? Because you have to construct it, you have to build a product. It might make this stuff even a bit also larger in some sense. Also, like in some cases, right, this can fail because this propositional translation from LTL to automata might make the symbolic game just too big. But like in the cases where you get more complex scenarios, right, this monitor approach can be very beneficial. These abstraction-based approaches and the direct approach, they just fail, right? Because you really want this additional reasoning. Okay, so to conclude, I hope that I convinced you that looking at this at the temporal logics in the context of infinite state synthesis is very interesting because they provide us with this higher level of abstraction to kind of efficiently specify things. And we've seen that like actually doing also already reasoning on this higher level structure, which has like this like more high level connection, already reasoning there can be beneficial for the overall synthesis process. And for that, I showed you our monitor-based approach, which allows us to solve the games later than more efficiently. Thank you for your attention.
Thank you very much. Question in the front.
Good talk. I really like the monitor approach. But I'm not quite familiar with the game literature on those games. So for the verdicts you mentioned, like are those common concept that has already been explored, or like they're new to this work?
What vertices do you mean?
Verdicts like the safety, unsafe, valid.
Okay, so I mean, the application of this verdict to this kind of game solving, this is kind of the main contribution of our work. Right? In some sense, you could even construct a monitor in a different way, right? I mean, you could still do this product, right? Because it's just as long as the properties are satisfied, it would still work in some sense.
I see. Thanks.
Question here and then in the back.
Great talk. I have this kind of curiosity question. Have you thought about coming up with a notation for benchmarking? So because obviously you use SMT in this context, you use LTL. Have you thought about sort of standardizing sort of notation? This is something I thought about, but I haven't seen anybody done that. Also for PSL.
This is currently work in progress. We have like a deadline in 1.5 weeks. We're writing a tool, and that contains exactly that.
Awesome. So, one question: where would you place the work on LTL modular theories, the reactive synthesis for that, in your classification, reduction, some set of tools, and symbolic tools on the other hand?
I mean, it's not like those things are, like strictly separated, right? So I would probably. I think it's something in between, right? It's not like for abstraction-based things and symbolic things. I mean, there are lots of techniques that kind of jump from one to the other, right? So it's not like I would say that you can always strictly classify in one of the categories. Does it answer your question, or?
And the other question is, in your example, you were using d prime equals d somewhere, but d is an environment control variable.
No. In this case, like this was also like some state, right?
In your formula, you have d prime equals d.
Yes.
D remains the same for it, but this is environment, right?
No. In this case, d is also state. This formula also doesn't have like an environment input. I mean, just to make the example simpler, because right, if you get environment, it gets more complex.
Then it's super simple. You just choose d 0, 0 less than 0. That's false, and then you're fine.
No. Like usually in our semantics, like the initial values of the system are chosen by the environment. So the initial state, right? You have to satisfy that for all initial states. But if you want to like have proper initial state, you need to have like an initialization step, right?
I think that is time, and thank you again for your talk.